much the same way that the chain rule for differentiation was reversed or inverted to create integration by substitution, we can do very much the same thing with the product rule. The integration version of the product rule is known as integration by parts. And just like the development of integration by substitution from the chain rule, we're going to start with the product rule for differentiation. The derivative of a product, f of x times g of x, is equal to the original function f of x times the derivative of the second function g of x, plus the second function g of x times the derivative of the first function f prime of x. So we start with this, and then using integration, we can turn it into a different form that will allow us to undo a product rule, so to speak. Now, before we do that, we're going to do a couple of things here that are going to make our notation a little bit easier. We're going to replace the function notation f of x with u, which will also, in turn, allow us to rewrite f prime of x as du over dx. We can do a similar thing with g of x and g prime using the letter v. So we're going to let u equal f of x and v equal g of x. This change in notation is done partially by convention, but also partially because it will allow us to see how the product rule for differentiation turns into the integration by parts formula. So now we're going to rewrite the product rule formula. Instead of f of x and g of x, we're going to write u and v. And on the right side, instead of f, we're going to write u. Instead of g prime, we're going to write dv dx. For the second term, instead of g of x, we write v. And instead of f prime, we write du dx. So this is just a rewritten version of the product rule. It's just rewritten with our new letters, our new variables. But right now it is the same old product rule. The next step then is to integrate. So we're going to stick an indefinite integral on each side. Now, note that because it is d dx, because the original functions f and g both had x as their input variables, when we are differentiating with respect to x, we also are going to be integrating with respect to x. And an interesting thing happens here. The dx's actually cancel out at the same time that the integration is canceling out with the differentiation, as we know from the fundamental theorem of calculus. So altogether, on the left side, that's going to leave us with just u times v. On the right side, we're going to have, again, the indefinite integral of, well, in this case, because there are two terms, I'm going to wrap them up in brackets. But we're again going to have the indefinite integral of the right side with respect to x. Using one of the properties of integration, I'm going to split this into two integrals. So the integral of the first term, u times dv over dx, with respect to x, plus the integral of v times du dx with respect to x. And much as happened on the left side, we're going to get some dx's canceling in each of these integrals, so that the right side is going to leave us with the integral of u dv plus the integral of v du. Almost there. One last step. We can rework this so that it ends up with the integral of u dv on one side And on the other side, we're going to have uv minus the integral of v du. A little bit of quick algebra will get us there. This is the integration by parts formula. It is meant to take an integral of the form u times dv. It is meant to take an integral of a product and produce an equivalent form on the right side. Now, at first, admittedly, it looks worse. Now, keep in mind that differentiation often produces something simpler than what we started with, if you think of things in terms of, say, the power rule. Very often the derivative ends up being a little simpler than what we started with. But the opposite is true with integration. Very often we end up with something bigger and more complicated than what we started with. And that is what the apparent case is here, that the right side looks like it's going to be more complicated. What actually is going to happen when we see this in examples is that the new integral, the v du integral, is actually going to come out to be a simpler integral than what we started with. Or in some cases, it might not be simpler, but at least it won't be any more complicated. Typically, it will be a simpler integral than what we started with, which means we might just be able to do that new integral outright without having to do any special tricks. So let's look at some examples of this. The idea here is that when we wish to use this for an integral of the form u dv, we're going to have to identify the two parts of it as u and dv. Now, the idea is that at the end result, we're going to want u times v minus the integral of v du. In order to write that, we're going to need u, which we will already have, and we're also going to need v, which we don't yet have, but that can be found very simply by integrating both sides of this dv, whatever it is. And I know that's very vague. We'll see an example in a moment. That will provide us the v that we need in the u times v term. It also will provide us the v we need in the new integral, the integral of v du. The other part of it we need, though, is du. And that is going to come from differentiating the u from the original integral. So again, to recap, the original integral is going to have two factors, and we need to identify one of them as u, and the other factor is dv. In order to produce all of the elements that we need for the equivalent form on the right side, we're going to need to take whatever we identified as u and differentiate it. On the other hand, we're going to have to take whatever we identified as dv and integrate it. So of the two factors in our original integral, one of the two factors is going to get differentiated, and the other factor is going to get integrated. How do we know which one's going to be which? Well, that's going to be different in every situation. But the basic rule is that you're supposed to make this simpler. You're supposed to end up with a simpler integral at the end than what you started with. To that end, we want to choose our u and dv so that they're going to become simpler. Or, in the worst case scenario, at least they don't get any more complicated. For example, suppose we have the integral of x e to the x dx. Now, first of all, there are no other integration rules we have that work here. There is no substitution here because there is no composition. This is not going to just fit the power rule for integration. It doesn't fit any of our basic integration rules, such as the integral of e to the x is e to the x. It doesn't fit any of those rules because of that extra factor of x. So what we have here are our two factors, x and e to the x. Now, one of those two factors has to be differentiated, and the other has to be integrated. E to the x can be either one of those. It can be differentiated, or it can be integrated. But either way, it turns into e to the x, which means that it will be the same level of complexity, regardless of whether we pick it for u and differentiate it, or pick it for dv and integrate it. So we're not getting any simpler there either direction. On the other hand, let's take a look at x. If we let u equal x and differentiate it, the derivative of x is just 1. So that definitely gets simpler. It reduces from a variable to a simple constant. That definitely is easier. On the other hand, if we integrate x, it becomes 1/2 x squared, which has increased in power and therefore gotten more complicated. So if it doesn't matter where we put the e to the x, and it does matter where we put the x, then we're going to pick it so that the x is in the place where it's going to become easier. Namely, we're going to let u equal x. dv is going to equal e to the x, along with the dx. The dx has to be attached there because in order to produce v, we need to integrate. And in order to integrate, we need a dx there. So if we attach the dx to the dv there, whatever factor we pick for dv, if we attach the dx to it, then we're ready and set for that integration. And as we already discussed, the integral of e to the x is e to the x. So it has not gotten any easier, but it at least has not gotten more complicated. On the other hand, on the left side over here, we have du dx is equal to 1. And to steal a page from what we saw in integration by substitution, if we multiply both sides by dx, we get du is equal to 1 times dx, or just du equals dx. So what we have here are the pieces that we need to assemble our integration by parts formula. Interestingly enough, we don't actually need dv in the integration by parts formula. We just need dv in order to integrate it to produce v. So what we now have is that the integral of x times e to the x dx by integration by parts formula is now equal to u times v minus the integral of v times du. And what you can see here is that the integral that we produced by using this formula is simpler than the original integral. In fact, we can now just do this integral directly. The antiderivative of e to the x is simply e to the x. And now all of our integration is finished, which means now it's time to stick that plus c on there. So the integral of x e to the x is x e to the x minus e to the x plus c. Now, that's not a very intuitive result. It's not immediately apparent that that answer is the antiderivative of x times e to the x. So a really good thing to do here is to check your answer by differentiating it. if we differentiate x e to the x minus e to the x plus c, it should produce the original integrand x e to the x. And without going through it here, I'll leave that to you. It does actually produce that. Further examples will help. Let's look at something where, again, we have a very specific choice for how we're going to set up our u and our dv. Suppose this time we have the integral of x squared times the natural log of x dx. Now, again, we have our choices. Our two functions are x squared and the natural log of x. Sometimes the very nature of the integrand will automatically direct us into how we choose our u and our dv. Like in the previous example, since it didn't matter where we put the dv, or where we put the e to the x, but it did matter what we did with the x, we let that guide us through it. We're going to have a similar situation here. Now, I'm going to start with the x squared because based on what we saw in the last problem, to either differentiate or integrate x squared is going to require the power rule. Ideally, we'd probably rather have x squared being differentiated because that will decrease the power. But if we're going to differentiate x squared, if we're going to use u equals x squared, that means we would need to have dv equals the natural log of x. So I'm just going to set this up for a quick moment, and suppose we choose it like this, knowing that the derivative of x squared will be simpler than x squared. The trade-off is that now we would need to integrate the natural log of x. And that should make you stop for a second and go, wait a moment. We don't know the antiderivative of the natural log of x, do we? So that kind of throws a whole wrench in the works. We can't have the natural log of x be our dv because we don't know how to integrate it. So we're going to have to go back and make a change. We now have no choice but to put the natural log of x as our u, because we can differentiate it. We cannot anti-differentiate it. That means we have no choice but to make x squared our dv, which, yes, we did say is going to make the power bigger. But it's still better than not being able to proceed at all. So it's not ideal, but it's what we have to do. Like with integration by substitution, if we know we're always going to have to move the dx to the other side, we can just do that automatically without an extra step. The derivative of the natural log of x is 1 over x, and then we move the dx to the right side. For v, we need the integral of x squared dx, which is x cubed over 3. And now we once again have the pieces that we need for the integration by parts formula. U, du, and v. Once again, the dv actually does not figure into the integration by parts formula. So, the integral of x squared times the natural log of x is going to be equal to u times v minus the integral of v du. Now, at first glance, yes, that looks like a worse integral than what we started with, except for the fact that the natural log of x is no longer in the integral. In fact, going a step further, we can even simplify some of those x's, and at the end of it, we actually have a simpler integral than what we started with. So we did achieve our goal of a simpler integral. It might not have seemed readily intuitive that that's where we were going to end up, but we did get there. Our last step then is to actually finish the integration. And again, once the integration symbols are all gone, that's when we stick on our plus c. And a tiny bit of simplification. And there we have it. And again, I will totally agree with you that this is less than intuitive. Looking at the original integral and looking at our answer, it's not readily apparent that that what we have is correct. So I highly recommend that you check your answer by differentiating it and making sure you're going to get the original integrand back. Integration by parts sometimes doesn't get you there right away. Sometimes it takes an extra step or two. Suppose our integral this time is x squared times the cosine of x dx. This is kind of similar to the first example, where the x squared definitely is better to be differentiated if we can get away with it. But if we needed to, we can integrate it. The cosine of x can be differentiated or integrated, and in either case, it's going to result in another trig function. If we differentiate cosine of x, we get negative sine of x. And if we integrate cosine of x, we get positive sine of x. So whichever way we go, we're basically going to end up getting the same thing. So much like the e to the x, with cosine of x, it doesn't really matter where it goes. So therefore, we can make our decision of u and dv based on the x squared. And as we already said, the x squared works better if we can differentiate it. And the cosine of x, therefore, doesn't really matter whether we differentiate it or integrate it, so let's integrate it. The derivative of x squared is, of course, 2x. And the antiderivative of cosine of x is, of course, positive sine of x. So once again, we have the pieces that we need here. Excuse me. And let's see how that does. So our integral of x squared times cosine of x dx is now going to be equal to u times v minus the integral of v du. To clean that up just a little bit, x squared times sine of x minus, at this point we can bring the 2 in front of the integral if we wish, the 2 times the integral of x times sine of x dx. Now in our previous two examples, after we did the integration by parts formula, it produced an integral that was simpler and actually that we could just integrate straight out. No special other techniques needed. That is not the case here. In fact, at this new integral, x times sine of x, is actually still a product. Now, admittedly, it is slightly better than what we started with. We started with x squared times a trig function. Now we're down to just x times a trig function. So we have improved it, but unfortunately we didn't improve it quite all the way there. So, as much as it stinks to hear this, we're going to need to do integration by parts a second time. So let's pull that out. And let's focus on the integral of x times sine of x dx. Well, last time we did this, we chose to make the x factor our u and differentiate it. We chose to make the trig factor our dv and integrate it. Well, it worked before, we might as well do it again. Just to clarify here, I'm now going to subscript my u's and v's to create a separation between what we did earlier and what we did now. Now, I also switched to a new color to help, again, further distance them in our minds so that we don't get them confused. You don't want to be using the variable u for two different things in the same problem. The same thing with v. You don't want to be using the same variable for multiple different things. So that's why the subscript. So du sub 2 is going to be now dx, and v sub 2 is going to be the antiderivative of sine of x, which is negative cosine of x. Now, this entire integral has to be replaced by the second integration by parts formula. So this is going to get a little hairy, but bear with us. Our original integral was x squared times cosine of x dx, and that produced the first term, x squared times sine of x, minus 2 times, and note the brackets, and this is where we're going to put our new integration by parts formula. U sub 2 times v sub 2 minus the integral of v sub 2 times du sub 2. So again, please note here the brackets. That 2 that was in front of that integral has to apply to the entire equivalent form of that integral. So yeah, it gets a little hairy with the algebra. So we now have x squared sine of x. If we distribute the negative 2 as we clean this up, this becomes plus 2x times cosine of x. And then we have the negative 2, the subtraction, and the negative in the cosine of the integral of cosine of x there. That's a lot of stuff to resolve. But the integral of negative cosine is negative sine. So we're going to have negative 2 times a subtraction of negative sine. And that's going to simplify to minus 2 times sine of x. And of course, the ever-present plus c. Now again, this is even less intuitive than the previous times around, but it does work. And if you want to, again, check by differentiating, it'll take a moment or two, but it can help make sure that you're getting the answer right. It can also help build your trust in the integration by parts process. So this is a thing also. Sometimes in doing integration by parts, it results in an integral that, while better than what we started with, still isn't quite ready to be done on its own and still needs integration by parts again. There's one other kind of really interesting situation that can come up with integration by parts. Take, for example, the integral e to the x times sine of x dx. Now, this is interesting. Part of what made e to the x, and in the previous example it was cosine of x, here it's sine of x, part of what makes them flexible in where we put them is that they are cyclical in their derivative and therefore their antiderivative cycles. E to the x is direct, its derivative and antiderivative are itself. And sine of x cycles through cosine and positives and negatives, but it does cycle and it remains the same level of complexity at all stages. So we're going to get an interesting thing when we try integration by parts here, because it doesn't matter where we put the e to the x, and it also doesn't matter where we put the sine of x. So I'm just going to do them in order. Now I'm going to start out by subscripting this because, as you may already have started to suspect, this is going to require more than one step of integration by parts. So we let our u sub 1 equal e to the x, so that du sub 1 is equal to e to the x dx. And we let our dv sub 1 equal sine of x dx, so that v sub 1 is equal to negative cosine of x. Now note, neither one of these got simpler. Neither one of them got more complicated either. And that's really the goal. You'd like things to get simpler than what you started with, but at the very least, you don't want it to get any more complicated. So while we didn't make it simpler, we at least did not make this more complicated. Time to go to our integration by parts formula. The integral of e to the x sine of x dx is equal to u sub 1, which is e to the x, times v sub 1, which is negative cosine x, minus the integral of v sub 1 times du sub 1. And just to clean that up a little bit, we now have negative e to the x cosine of x minus, and then we have a negative sign inside the integral, so we can now bring that out front and turn this to plus the integral of e to the x cosine of x dx. Like the previous example, this new integral is not any easier than what we started with. I mean, at least in the last one, the power on the x dropped by 1, but we still had to do integration by parts a second time. That is certainly the case here. We ended up with an integral that still has a multiplication in it, so we need to do integration by parts a second time. So now we're going to take that out. And do integration by parts again. Like the previous example, whatever we did the first round of integration by parts, we might as well do it again. Because, again, even if it didn't make it better, it certainly didn't make it worse. So I'm once again going to pick e to the x as my u, and once again pick the trig function, this time it's cosine of x, as my dv. Du sub 2 is, again, e to the x dx, and v sub 2 is going to be the antiderivative of cosine of x, which is sine of x. So we have our original integral of e to the x sine of x dx is equal to negative e to the x cosine of x. That was the first term of the first integration by parts run through, plus the second integration by parts run through, u sub 2 times v sub 2 minus the integral of v sub 2 times du sub 2. To clean that up a little bit, and what you may notice here is that because of the cyclical nature of the derivatives and antiderivatives of both e to the x and sine of x, we actually now have the same integral that we started with has shown up again over here. Now, at first, you might look at that and go, well, that's kind of annoying because we're right back where we started, but we also have extra stuff. Well, we're not exactly quite back where we started because now what we have is the same term on two sides of the equal sign, which means they can be moved to the same side and combined. If we add this integral to both sides, we actually get 2 times the integral of e to the x sine of x dx is equal to negative e to the x times cosine x plus e to the x times sine x. Which means we can actually get an end result of this. Because what we're looking to do is find out what is the integral of e to the x sine x equal to. Well, divide both sides by 2. Or multiply both sides by 1/2 if you prefer that. And at long last, we can stick our plus c on the end. And there we are. We have taken the integral of e to the x sine of x dx and produced a result that no longer has any integration in it. And again, far less than intuitive. I encourage you again to check your answer by differentiating it. So what we get out of all of this is that sometimes we're going to have to do integration by parts more than once. Sometimes it will result in an integral that is no better than what we started with, but hopefully not any worse. So we keep going. And you might have to do it 2 or 3 or 4 times or more. Now, I'm not cruel enough to give you a test question that's going to have you do it 4 times, but the idea is that you can continue to do it. The idea of the integration by parts formula is that it is supposed to give you an alternative equivalent form to the original integral that you can then work with the new integral, and hopefully it will be an improvement on what you started with and therefore easier to work with. And in the case that it doesn't get any easier, keep going and you may get a situation like this where you actually see the original integral appear on the right side as a result of one of the iterations of integration by parts. Now, here's one last use of integration by parts here. Not a weird situation that comes up, but just a use for it that you might not have considered otherwise, because we describe integration by parts as being used on an integrand that is a multiplication of two things. It actually can be used on integrands with a single factor, such as the antiderivative of the natural log of x dx. That's actually a little bit misleading. The integrand never has a single factor in it because the dx is always a factor. If you remember the Riemann sum formula, which when we put a limit in front of it, that's what became the indefinite integral, or the definite integral, the dx came literally from a multiplication by delta x, which then turns into a multiplication by dx. So there are always two factors. In this case, we let the single factor, as it were, be our u, and then our dv is just going to be the dx by itself. So the derivative of the natural log of x is 1 over x. And the antiderivative of dx is just x. Much the same as the antiderivative of dv is v, the antiderivative of dx is x. So our integral of the natural log of x dx is going to be equal to u, which is the natural log of x, times v, which is x, minus the integral of v times du. And much the same as our second example, we actually see a simplification in this integral where the x's cancel out, and what we're actually left with is simply the integral of dx, which, well, we already talked about. The integral of dx is just x. So integration by parts transcends the obvious version of, hey, I have two different functions being multiplied here. It can be used on what can be looked at as a single factor. Now, most times we wouldn't have to do this because we have ways of integrating, say, a single factor like sine of x or a single factor of x cubed. We can integrate those things directly. But then there are things like the natural log of x, or perhaps even the inverse trig functions, like, say, the antiderivative of the arctangent of x. Now, we have no idea what the antiderivative of the arctangent of x is. We don't know. We know what its derivative is. From Calculus 1, you know what its derivative is, which makes that a good choice for our u. And since there's only one factor, well, there's always a second factor. The dx is just going to be our dv. So again, we do know the derivative of arctangent. You can look it up if you have to, but you will want to make sure that you know these things pretty readily. The derivative of arctangent is 1 over 1 plus x squared. And of course, the antiderivative of dx is just x. So we have u, which is arctangent of x, times v, which is x, minus the integral of v, which is x, times du, which is 1 over 1 plus x squared dx. To clean this up just a little bit, we'll make the first term x times arctangent of x. And the second term, the integral there can be written as a single fraction, x over 1 plus x squared times dx. Now we have an integral that is completely different than the integral we started with. It doesn't look at all the same. In all of our previous examples, the integral that we ended up with looked pretty similar to what we started with. Maybe with the exception of the ones that included the natural log. But most of the others, the integral looked very, very similar. In this case, it looks completely different. In fact, this doesn't even look like a product anymore. It was written as a product to begin with, but it doesn't even really look like one when we write it as a single fraction like this. But we do have other integration techniques that can come into play. We now have a brand new integral. We shouldn't necessarily look at it as always thinking, hey, since I started with integration by parts, that means I'm going to have to use integration by parts at every single step. Actually, in this case, substitution is the way to go. Now again, I don't want to double up on variables, so I'm going to switch to use w here. If we let w equal 1 plus x squared, then dw would be 2x dx. Or if we divide both sides by 2, we can have 1/2 times dw is equal to x dx. And that will allow us to rewrite this integral. Now we've still got the x times arctangent of x in front of it, but this will allow us to rewrite this integral as 1/2 times dw, and that is going to replace the x in the numerator and the dx off to the side. The 1 plus x squared in the denominator is going to be replaced with a w in the denominator. Let's get that 1/2 out of the way. And let's rewrite. No, excuse me, we actually don't even have to do that. We can leave this as 1 over w dw, because then it's going to turn into the natural log of w. At this point, we can throw on our plus c since all the integral symbols have disappeared. And for a last step, we re-substitute to get it back in terms of the original variable. And there we are. Again, not obvious. There's no way you would look at this answer and go, oh yeah, that is clearly the antiderivative of arctangent of x. But if we trust the process of integration by parts, and also, as it turned out, the process of integration by substitution, we can certainly get there.